All right. So now we're going to see a couple that explain really how large language models work. And I was very happy to get this under control. So BERT is a bidirectional encoder representation model. It's one of the pre-trained large language models. And one thing that really confused me when I learned about large language models is how do they convert the words into numbers? And how do they convert the words into numbers that are representative of their meaning? Because similar words will have similar vectors, and different words will have the difference in meaning between words is actually encoded as a numerical distance. And I wondered how they could do that without paying people to like encode those words. And this is how they do it. First, you tokenize the sentence. And in some models, you use smaller fragments, but here we're going to use pretty much just the words as tokens. So we have a couple sentences. We say Napoleon revolutionized military organization. So to tokenize it, you just assign numbers to the words, and you have extra tokens like the start of a sentence, CLS. And these are just meaningless random numbers. That's tokenizing. Then you do the part that matters. You embed it in a high-dimensional vector. Each word turns into a vector, and these words are meaningful. These vectors are meaningful in the sense that two words with similar meaning will be near each other in this vector space, and two words with different meaning will be far apart in this vector space. And so here's how it works. Here's some code which will show how to encode three words. So this is going to import the pre-trained BERT tokenizer, and it's going to take these sentences, Napoleon revolutionized military organization. Notice the ized is a separate token, so it's not exactly one token per word, but it's close. Then Napoleon has legacy, period. Legacy still lives, period. Three sentences with some words repeated across these sentences so you can see the effect. And those will come out tokenized. You'll see them here. So 101 is the starting mark. Then Napoleon revolutionized military organization. Then the period gets a token of 1012. The next time Napoleon comes, it's got the same number. The period has the same number, and so on. This legacy and that legacy have the same number. So it's encoded it's encoded the tokens as numbers. Now, the way it learns meaning is through masking. And it doesn't actually learn meaning. What it learns is relative meaning. The LLM does not know what the words mean. It doesn't even know there is a world out there or that these words are symbolic of real things, but it does find the relationship between words in the sense of the likelihood of one word being near another. So what this is going to do is mask 15% of the words randomly and then train a large learning model to predict the missing word. This is how you create labeled data from unlabeled data. You know what the right word is, so you can tell it to practice guessing the word until it gets the right word. And so here's the masked version. It's going to put these 103s randomly in place. So it's masked out three of these words. These two words and that one, and it's going to try to guess what will happen to fill them in. That's how it works. And BERT has already learned a whole vocabulary of like most of the English words. So we can now try to predict a masked word. And this is one I've shown in the lecture before. This is where I got that image from this project. So I have the sentence, artificial intelligence mask take over the world. And the BERT pre-trained model will calculate what the most likely words are to go in where the mask was. And so here it is. You have a 30% chance of it being can, artificial intelligence can take over the world, an 18% chance of it being artificial intelligence will take over the world, 5% for to, 4% for pounds. Oh, just S, artificial intelligence as, just adding an S to the word, and so on. So and all these are reasonable sentences. And that's the point. It knows how to pick a word which is likely to be there, predicted from the words around it. That's why sentences in large language models read smoothly. They have the words that a normal human would expect to fill in there. So now the next part, to make a larger scale than a sentence makes sense, you use sentence masking. You have a sentence and then a sentence after it, and half the time you replace the sentence after it with another random sentence. And then you try to detect whether that has happened or not. Is this the right sentence or the wrong sentence? And again, you've created mass labeled data from unlabeled data, so you can tell the model can practice and learn what order sentences should be in. So that's this one. It has this attention mask and this token type ID that shows this is the first sentence labeled with 0. This is the second sentence labeled with 1. And it will replace the second sentence randomly with the wrong sentence and train it. That's all it does. That's why I say it simulates intelligence. It makes sentences that you can read that looks smooth, and it makes paragraphs that read smooth because it knows the sentences should have sentences near them that are in context. So it creates something that looks like a human wrote it without any comprehension of what it's saying. And now we can test it for sentiment analysis. One of the useful things here, this is what the intelligence agencies are getting military LLMs for now. You have a flood of data, like all the newspaper articles and other information you have coming in, and you want to summarize that saying, is this political event likely to happen today? Is this guy going to get deposed? Something like that. I want you to summarize all this information and tell me. So we're going to test it with movie reviews. This is going to download a database of movie reviews, and they come with like a rating of stars and then paragraphs describing what they think of the movie. Here's an example. One of the other reviewers has mentioned a wonderful little production. I have 100 movie reviews, and it has narrative, sentences describing the movie, and then it has a number of stars, which we're going to summarize as positive or negative here. And so we want to do sentiment analysis with BERT. It's going to analyze the movie reviews and decide from the narrative whether that movie review, from data without sentiment, they're going to decide whether it's a approving review or a negative review. So it downloads all this information to run the BERT pre-trained model. And then it's going to cough up a sentiment value. It's going to put out a number here at the end, which is from very negative to very positive, 1 to 5. Which is, it's originally determining how many stars to give the movie from 1 to 5 stars. That's what this model does. It's pre-trained to do that. So I'll just let it run and talk about it here. So when we're done, we're going to, now what we have, the original data told us whether it was positive or negative, but the model gave us 1 to 5 stars. So I decided to call it only wrong. I said if it's 3 stars, I'm not going to call it wrong either way, because that can be positive or negative. But if the sentiment is positive, but the stars is 1 or 2, then I'm going to call that an error. And if they said the review was negative, but it was really 4 or 5 stars, I'm going to call that wrong. That's how I'm going to evaluate how many it got wrong. So here you go. Here's the example. The original data was like this. It had these things, and it told you whether it was positive or negative. The model said, this is 2 stars, this is 5 stars, 1 and 4. So now I can evaluate the accuracy of the model, deciding how many times it got the sentiment wrong. Out of, I think, 100 reviews is what we're doing here. And so you can see it got 6 wrong out of 100. So BERT is pretty good. This pre-trained model is pretty good at telling whether things are positive or negative. All right, so that's the first thing. They get some practice of seeing how it encodes words and uses words. That is encoding. Let me stop this video.